why were logarithms even invented? And the purpose of logarithms is when you are provided an equation and you need to solve for a variable, but that variable is in the exponent position, and doing mental math does not allow you to find the exact answer. That's why we have logarithms. So you may have get an answer like this, but it's not necessary for us to use logarithms here. We could use them, but we know the answer is x equals 2. In this problem, a common misconception for number one, logarithm equations, try these. A common misconception is 5. Students think 4 times 5 is 20. Notice that the x is in the exponent position. So how do we solve? Whatever we do to one side, we must also do the other side. So I'm going to do log base. I want to get rid of the 4. So log base 4 to both sides. And now I'm going to bring down exactly what was previously there. So we have 4 raised to the x equals 20. That pen is not working very well. Let me switch to a pencil, which I dislike using. On the left-hand side, log base and 4, we see they cancel out, and you can think of that if you want, but in reality what it does is it really simplifies down to 1. This simplifies to 1, and this exponent actually drops down in front, and you may have seen that in a previous video from lesson 4 in the triads when I explained it. So any exponent is going to drop down. It doesn't matter if it's x plus 1. Any exponent here is going to drop down in front. So x drops down in front, and I have log base 4 of 4, and this equals 1. Now, why is that? Because think to yourself, 4 raised to what number equals 4? 4 raised to, I don't know, equals 4. The answer is 1. So this is equivalent to 1. And 1 times x is simply x. So that's a mathematical understanding. A lot of times students will just see, okay, when this log base and the number behind it are exactly the same, I know that it cancels out, and whatever the exponent was just drops down. So a lot of students will do that procedure and not understand the math. I just explained the math to you and why it actually occurs. Now I'm thinking over here to myself, can I do mental math? 4 raised to what equals 20? I don't know. So I grab a calculator. Let me clear it so everybody can see it. And since the base is not 10, I'm going to hit math. I'm going to go up 3 times. Base is 4, number behind it is 20, and I get 2.12. 2.12. We rounded that to the nearest thousands. It probably would be 2.121. Mr. McFarland tends to change. That's the answer keys you have between rounding to the thousands or hundreds, but there's not always an explanation which one to do. Again, for any assessment you do, I'll tell you what to round to, so there's no question about that. Let's look at number 2. Let's take a look now at number 2. Taking a look at number 2 as I'm trying to solve for x. I explained earlier in this video why we even have logs. Remember, E is Euler's number. E is not a variable. So I'm going to start by doing PEMDAS backwards. I'm trying to solve for the x. So on the side that has the variable, is there any adding or subtracting that can be eliminated? 2 times e to the x equals 12. Divided by 2 gives me e to the x equals 6. And now I'm back to an exact same problem like number 1. I have a value raised to a variable equals a value. A value raised to the variable equals a value. To eliminate the e, I'm going to do log base e. Whatever I do to one side, I must also do to the other side. Now, I'm going to show 2 ways of doing this, knowing that you're first learning logs at this point. So at this time, as I shared with you before, the mathematical understanding is that any exponent to this value now just drops down directly in front. It's being multiplied by it. So I have x times log base e to the e equals log base e to the 6. And whenever a value whenever the base is exactly the same value as the number in back of it, this simplifies to 1 because it means e raised to the what is e? 1. So this value is 1. So I have x times 1 on the left, which is simply x. A lot of students, as they go through this multiple times, when they get to this point, recognize that this is simply, you want to say sometimes cancel out, but really it simplifies to a 1. I want you to have the mathematical understanding. So this simplifies to the 1, and we drop down whatever is the exponent. In this case, it's the x. Now log base e of 6. Okay, now at this point, I'm thinking to myself, what do I do? Remember log base e and ln, natural log, they're interchangeable. Oops, sorry. So on my calculator, I can find ln down below. I'm going to type in ln of 6. I don't have to do ln with a base because ln has a base. It's the same as log base e. And so we have an answer here if I round it to the nearest thousands, which would be 1.792. 1.792. Let's take a look right now at number 3. 10 raised to the x plus 3 minus 4 equals 6. I'm going to add 4 to the opposite side, and I have 10 raised to the x plus 3 equals 10. And I recognize that when I just see the value 10, it's the same as 10 to the first. Now, number 3 and number 4 are different than 1 and 2. 3 and 4 are similar. When you have the exact same base on the bottom and there's no additional adding, I'm going to give you an example of what that may look like. So 10 raised to the x plus 3, and if we had like a plus 5 here, we could not do this in the same manner. So there can't be an additional numbers that were being added or subtracted here or multiplied in front. We don't have that. We have 10 raised to some value equals 10 raised to the first. When that occurs, there's a shortcut to solving for x. We are able to cancel out the exact same bases and drop down what was in the exponent position. X plus 3 equals 1, subtracting 3, I get x equals -2, and I always like to go back and make sure this works. So if I come up here and I plug in -2, I have -2 plus 3 is 1, 10 to the first is 10, and 10 minus 4 is in fact 6. Correct answer is. Let's take a look at number 4. Number 4, I'm going to start by subtracting 5 from both sides. I get 2 raised to the 3x minus 1 equals 8. And in my mind, I'm thinking to myself, how can I rewrite 8? 2, having the same base, 2 raised to what value? Is it possible to get 8? So I'm going 2 to the first is 2, 2 squared is 4, 2 to the third, 2 times 2 times 2 is 8. So let's rewrite this as 2 raised to the 3x minus 1 equals 2 to the third. Now, just like number 3, when the bases are the same, they cancel out. I have 3x minus 1 equals 3. Adding 1 to the opposite side, 3x equals 4. Dividing them by 3, I end up with x equals 4/3. X equals 4/3. We have number 4. Let's take a look right now at number 5. So number 5 here, I'm going to go back and I'm going to write this as exponential. I take the base, I raise it to the value on the opposite side of the equal sign. In this case, it's 5. And I go right back to the left, equals x. 2 to the 5th is not 10. It means 2 times itself 5 times. So 2 times 2 is 4, times 2 is 8, 16, 32. X equals 32. X equals 32 would be the correct answer for number 5. Let's take a look right now at number 6. A look at number 6. Give me 1 second here. Okay, number 6, we have 3 log base e of x minus 2 equals 7. Notice there's no parentheses. When there's not parentheses, this is one section. So let's try to get that one section by itself. And when I want to isolate this, I did have to do PEMDAS backwards. So first I start by adding 2 to both sides. Log base e of x equals 9. Then I take and divide both sides by 3. Log base e of x equals 3. And now I can change this into exponential form. I take the base, which is 3. I raise it to the opposite side. Sorry, I take the base, which is e. Euler's number, it's e. I raise it to the value on the opposite side, which is 3. And I come back equals x. Well, I don't know what e to the third is, so we're going to go second. Euler's number shares a key with ln. I do have to hit the blue button first to the third. And if I round this, I come up with an answer here of 20 point, what does he want us to round to? 20.085. Let's go on to number 7. Let's move on to number 7 here. And I can see at his answer key, he leaves it just like this. Again, the other ones he rounded to the nearest hundredth or thousandth, so I would prefer you round it to the nearest thousands. I will make sure that any assessment, you're told exactly what to round to so there's no confusion. Let's look at number 7 if I have room to do it in here. Let's look at number 7. Okay, number 7, Same thing here is I want to isolate this portion. This is not in parentheses, so I have 8, subtract 2, and then there's no parentheses behind it here, no value, so it's log base 3 of x equals 2. First, I'm going to subtract 8 to both sides. Negative 2 times log base 3 of x equals negative 6, dividing by negative 2. Log base 3 of x equals 3. And this one I can do by going 3 raised to the third power equals x, putting in exponential form. 3 raised to the third power equals x. And 3 raised to the third power is 27. 27 equals x. Let's go into our last problem from this try these. Now I have it in parentheses. So 6 subtract 2 times log base 10 of 8x plus 4 equals 2. I want to get this portion by itself. I'm doing PEMDAS backwards, so first I'm starting by subtracting the 6, log base 10 of 8x plus 4 equals negative 4. Now dividing by the negative 2, log base 10 of 8x plus 4 equals 2. 10 raised to the power of 2, 10 raised to the power of 2 equals this quantity, 8x plus 4. Well, 10 to the second power is 100. And now to solve for x, I'm going to first start by subtracting 4. 96 equals 8x. And if I take 96 and divide it by 8, I get an answer of 12. X equals 12.